Hello friends, well this lecture or this presentation will be all about static and dynamic loading and the related concept of strain energy. Now how is static and dynamic loading different? Let us try to explore this. For example, let us suppose that there is a wall like this and there is some kind of a prismatic bar attached to the wall, and this is some kind of, suppose, a loading arrangement. Now I decide to pull this prismatic bar, and let us suppose that at a point I apply a force P, and the corresponding deflection at the force P is, suppose, this is equal to delta. Now this is a case of static loading wherein there is no sudden application of the load. Suddenly I am not applying P at time t is equal to, say, 0. I am not doing that. Rather what I am doing is that I am slowly incrementing the load, I am slowly increasing the load, and at every point equilibrium will be necessarily maintained between this load and the elastic restoring forces of this prismatic bar. So at every point, if equilibrium is maintained and there is an application of load from 0 to P with a corresponding increase in deflection to 0 to del, then we have a case of static loading. And now let us try to find out the related concept of strain energy. What is strain energy basically? Now strain energy is some sort of the stored potential energy in the form of work done on a body till the proportional limit, right? Till the point the body is elastic, right? So the strain energy is the summation of all the work done, right, to bring a body from an unstressed state to a deformed state, that is till the body is elastic, right? So strain energy is the summation of all this work done. Now let us try to understand the whole concept of strain energy theoretically. Now for example, if we have some kind of a graph like this, and this is, suppose, delta, which is plotted on x-axis, and this is P, that is plotted on y-axis, then we know that till the proportional limit or the elastic limit, P is necessarily proportional to delta, and that is, this two will have some kind of a linear relationship. So till P, till this point, that is, let's say, proportional limit, we have the value of P to be proportional to delta. Now let us say this is one value of P, suppose P dash, and the corresponding value of delta at this point is nothing but delta dash. Now I increment the load because it's a case of static loading, and we slowly increment the load to point P, suppose. For example, if this is P and this is, suppose, delta, then we slowly increment the load from 0 to P with the corresponding deflections plotted on the x-axis. So if we increment the load by, let's say, dP dash, the corresponding deflection will be nothing but is equal to d delta dash, right? So essentially the work done by this force P dash to produce the displacement d del dash will give me the work done that is stored in the form of a potential energy on the body, that is the strain energy. So work done is equal to nothing but P dash into d delta dash, right? Now the summation of all this work done from 0 to this point, the proportional limit, will basically give me the strain energy. So strain energy is the integration of P dash into d delta dash, and as it can be easily seen that this is this portion, that is the area or the region below the straight line, right, gives me the strain energy. So that is basically half into P into del, right? So the total strain energy that is stored in the body to bring it from an unstretched state to a state wherein there will be the maximum elastic deformation is basically strain energy, which is stored in the form of potential energy, and this is equal to P into delta by 2, wherein P is the load at the proportional limit, delta is the deflection at the proportional limit divided by a factor of 2. So essentially now we got to rub this figure, and if I say that strain energy denoted as U is equal to nothing but, suppose, P delta by 2. Now what is delta? Delta, as we know, delta by L is equal to P by E, right? Sorry, stress by E, and stress is equal to P by A. So delta is nothing but PL by A, right? So if we can substitute delta as PL by A, what we have is here P squared L by 2A. So this essentially gives me strain energy as a function of P, or the function of load. But on the other way around, if we substitute the value of P by delta, then what we essentially have is AE delta squared by 2L. So this gives me strain energy as a function of delta. Right. So strain energy, number one, can be expressed as a function of load. It can also be expressed as a function of deflection. Right. So the next concept is about dynamic loading. Now, how is dynamic loading different from static loading? Let us see. Here, I will draw another simple arrangement wherein this is again a wall and this is again a prismatic bar. Right. But this prismatic bar has some kind of a bottom flange like this. Right. Now, I attach some kind of a weight. Right. It's like a case of monkey hanging from some kind of a tree and it's falling, right? And this is suppose my weight. And this weight, by an arrangement, if we leave it